So yes. Okay. So I'll talk to you today about some joint work I did with Patrick Lipka-Bartosik. So Patrick has just finished in Bristol actually, and he's in the process right now of moving to the University of Geneva to go and work with Nicolas Brunner. And Patrick did a lot of the work in this project. He did lots of the heavy lifting, but it's a pleasure to present the results that we kind of obtained together about catalysis in quantum thermodynamics, which is a topic I find very interesting. And my view is that this is kind of the beginning, hopefully, of something, definitely not the end. So a brief outline of my talk. So especially given that I'm the first talk of the conference, I'll try to give what I hope is a kind of a relatively broad introduction to a resource theoretic approach to quantum thermodynamics. So this is one approach which has been relatively popular over the previous years. And within this approach, there's an interesting phenomenon known as quantum catalysis. So I'll explain what this is. Should be relatively intuitive, but it's something which kind of occurs. And so, yeah, Patrick and I were interested in kind of how universal were catalysts, or how specialized do they need to be. And we have kind of two results, which I'll outline briefly. So on the one hand, we have some kind of analytical results to do with when you have multiple copies of a state. And then moreover, we looked kind of quite carefully, Patrick did a lot of numerics, looking at how much more general this result is. So obviously we wanted to say as many things analytically as we could. This appears to be tricky as far as we could tell. We spent a long time working on this project. So we have some numerical results, and I'll talk about where I think that we could go in the future, for example, extending the analytical results and many of the open questions which I think arise. Okay, so let me begin by giving you an introduction to this so-called resource theoretic approach to quantum thermodynamics. This is a framework I think is most suited, really. The motivation for this framework is if you want to study kind of really fundamental limits of quantum thermodynamics. And I say this because it's a very kind of highly idealized framework, and it's very powerful. And so you allow yourself a lot, and then if you find that there are restrictions with what you can do, then of course these are kind of fundamental restrictions, which, and there's been lots of work going beyond this and other frameworks. So this is not the only framework, but it's one which, as I said, I think has been relatively powerful. It turns out it was put forward in a paper by Jansing and other authors back in 2000, and it was kind of rediscovered, or popularized a lot in this famous paper from 2013 by Brandau, Horodecki, Oppenheim, Reens, and Beckens. Okay, so in any resource theory, so quantum resource theories, I'm sure most of you would have heard of them. They're kind of something very, very popular and in fashion at the moment. And broadly speaking, there are three main ingredients of kind of any resource theory. And the prototypical resource theory, where this all kind of started, was the theory of entanglement, somehow thinking about entanglement as a resource. So what are the three ingredients in thermodynamics? Hopefully you'll feel that these are very natural. So on the one hand, we need something free. And so in thermodynamics, what's free? Well, a thermal bath is kind of the thing that's free. It's kind of useless. It's not that interesting in itself. And so in this resource theory framework, this would be, say, some collection of particles or one particle. You can kind of take whichever you like. You'll have some arbitrary Hamiltonian. So this is, as I said, it's kind of a highly idealized and powerful framework. So you tell me your Hamiltonian, and that's kind of fine. And the state I'll give you the thermal state, or the Gibbs state of that in that Hamiltonian. So I give you say I'm calling it tau beta of HB, would just be the standard Gibbs state. And just to say, there's kind of one fixed global background ambient temperature, T, and corresponding inverse temperature, 1 over kBT, which we're calling beta, right? So this is a kind of our ambient temperature. So we have access to this free object, a thermal bath, and I kind of assume that I can just prepare at will any state as long as it's thermal. So this is the kind of mentality we're using. Now, the second ingredient in any resource theory is kind of the opposite of this. So if you have something's free, you don't want something which is resourceful. So anything, what would be a resourceful state? Well, that would be something which is out of equilibrium. So, you tell me it's Hamiltonian, HS, S for system. And now if you give me, if the state of the particle is any, say, density operator rho S, which is not equal to its thermal state, then this would be a state which is out of equilibrium. And so we'll think about this as a resource. So again, this is very much in line with how we tend to think about thermodynamics. We're not doing anything too different here. And And then finally, what are the interactions? So typically you need free states or free objects, resourceful objects, and then some way of some set of allowed transformations some set of allowed transformations. And in this context, what do we allow? So we allow any energy conserving interaction. So in other words, if I think about the total non-interacting Hamiltonian of the system and the bath, HS plus HB, we allow ourselves to do any interaction between the system and bath, which commutes with the total Hamiltonian. So the logic behind this is that we're allowed to shuffle energy around, but we're not allowed to inject energy in or take energy out. And also entropy, right? Because it's unitary. So this is kind of a big closed universe where entropy and the energy of the system plus the bath is fixed and constant. And so we can the idea is I can bring them into interaction for some fixed amount of time. I do the interaction in a very controlled way, the interaction I want, and then I pull them apart and now they're no longer interacting. So as I said, it's very idealized. That's what we just have to accept, but this is the framework I'm going to work in. Okay, so these are the three main ingredients. And so what is a basic question that we're interested in kind of thermodynamics more generally, but it is the idea of a state transformation, right? So we're interested in processes. So I have some system which is out of equilibrium and I might want to take it to maybe I want to thermalize it to bring it to equilibrium. Maybe I want to transform it to another state also out of equilibrium. So we're generally interested in these kind of transformations of state. And so the terminology that people use in this framework of the resource theory, they talk about thermal operations. And it is essentially what I just described. So you have your system and your bath. You prepare your bath in whatever state you pick the Hamiltonian of the bath, and then you assume that you have access then to its thermal state. You interact them using some energy conserving unitary on the whole, and now we kind of forget the bath, we throw it away, and so we're interested in what's the final state of the system, right? So this entire operation of bringing the bath, interact, and then trace out, I can just denote this as some transformation at the level of the system alone, which I'm calling TS of rho s, and this gives me some final state sigma s. And what we write, just to kind of keep the notation a bit simple, is I say, if there is a bath and there is some unitary which transforms rho into sigma, then I'll just draw a little arrow and write thermal operation on the top just to say that this is possible, right? So this is just a simple way that I'll use in this talk just to denote that rho s can go to sigma s. And in general, the question we're interested in is which transformations are possible, right? So, which state transformations can I achieve? And if you like, this is essentially, getting at the content of the second law, right? So, we know that it's impossible if you're at thermal equilibrium, you shouldn't be able to get out of thermal equilibrium. That's a statement of the second law, and we know that the free energy should decrease. In general, that's a different type of statement of the second law, and this is a similar type of statement in this quantum regime to say, well, what transformations are possible? And so for quasi-classical states, so in other words, states which are diagonal in the energy eigenbasis, so states which have no coherences between different energy levels, that we have a complete characterization of these transformations, and it's characterized by something called thermomajorization. And this was found again in this relatively famous paper by Horodecki and Oppenheim, which came out, roughly at the same time as the resource theory was introduced. For non-quasi-classical states, it's more complicated, but so this is why I'm just going to stick to the minute to keep things simple to quasi-classical states. And actually all of my talk, all of the results will be about in this regime. So something we would like to do is go beyond it, but I think this is challenging at the minute. So as I said, normally people phrase this in terms of thermomajorization, but actually I like to phrase it in a slightly different way. Not a result of mine, but there's a nice paper by Joe Reens, where he actually shows that thermomajorization, you can phrase it in an entropic form, and you'll see in a minute why I like this form. So there's a kind of a continuous set of conditions which have to be satisfied for all parameters epsilon in this range. I need that this so-called hypothesis testing entropy, relative entropy of rho to the thermal state, should be bigger than the hypothesis testing entropy of sigma to the thermal state. The definition need to worry too much. This is an entropy which has appeared in quantum information a kind of a long time ago. it's an interesting entropy. It's the entropy associated to doing a binary hypothesis test. So the reason I like this formulation is because it kind of shows that in some sense, it shows that there's a kind of strengthening of the second law. So instead of just having one condition to say whether or not a state transformation is possible, I need to satisfy this kind of continuous set of conditions, and they're all entropic in nature. They're all relative entropies. And I think this is a nice way of thinking about this thermomajorization result. Okay, so this is just the kind of very, very basics, some of the key results of the approach to thermodynamics. Okay, and yeah, as I said, this can be seen as a refinement of the second law. This is the kind of way to think about this collection of conditions here. Okay, and so now let's think about catalysis. So far I haven't spoken anything about catalysis, but let's think about what that might mean. And so if we take a very kind of broad view just for a moment, if we think about a thermal machine, think about, even very, very classically, you think about a steam engine or a fridge or whatever kind of thermal machine you think of. So there's always these two ingredients, right? We have the working substance, the thing which, say, the gas which is expanded and compressed, but then you have everything else. You have the piston and all of the machinery which kind of is containing the gas, and that machinery is necessary, right? We can't just take a gas and expect it to be able to do a Carnot cycle. We need the rest of those objects, and so the rest is, it might degrade very slowly, but generally speaking, we can kind of think about this as an auxiliary system, which is returned at the end of the process in exactly the same state as initially, right? The container that contains the gas and the piston that's pushing the gas in and out is kind of there. We use it, but it's returned. And so we can think about this as being a catalyst. And this is a bit more general maybe than if you think to catalysis as something you might have learned about in chemistry. This is a kind of a broader view of what really is a catalyst. And I think this is a nice view to take. And so, maybe the way I phrased it already, it seems pretty obvious that do catalysts help in quantum thermodynamics? Well, in some sense, we should expect them to help, because it's kind of very natural that we have catalysts in classical thermodynamics too. And so the answer is yes, they do help, and they help in a very nice kind of mathematically clean way. And so what we're going to do in this resource theoretic perspective, so I'm going to build up to explain a bit more how they help, but in this resource theoretic perspective, I'm going to give myself access now to another system. So for example, it might just be one more particle. And again, I'm going to take a very powerful approach, and I'm going to say, well, it can have an arbitrary Hamiltonian. And this is now going to be a kind of a fourth ingredient in this catalytic kind of resource theory. And the requirement I have in order to have this, the special requirement on this system is that it must be returned back in its initial state at the end of the process. So when I do my thermal operation, I can't kind of change it. I don't want to use this to cheat. I don't want to use this as a source of energy or as a source of low entropy. I really want to make sure that it's being used in a more interesting way than this. And so my picture would be something like this. So we'll have the heat bath as before, have my green system, and now I've got my purple catalyst, and now I'm allowed to do some big energy conserving unitary on the whole. So this would be something that now the total Hamiltonian, the bath, the system, and the catalyst. Okay, and so because of this, we essentially get what a priori should be a new set of transformations, right? So we can call this catalytic thermal operations. And so now this will act on the system and the catalyst. I give you the pair, and they're initially going to be uncorrelated. I bring in a thermal bath, I apply some big unitary, I apply some big energy conserving unitary, and I trace them out at the end. And I have this requirement, you see here at the end, I want them to be in a tensor product, and I want the same omega c to appear. So rho has transformed into sigma, but omega c has remained omega c, right? So it's remained in the same state. And as I said, if you want to think about this, you might think about this as being the rest of the machine, the rest of the thermal machine, the walls of the cylinder or something like this, and maybe this is helpful. And so there are two things just to say. So on the one hand, the catalyst is left unchanged in the idealized case, and also you see there's no correlations here. So I'm really demanding that the final state of the system is not correlated with the final state of the catalyst. This is what you want in the ideal case. And so now we can kind of update up my notation from before, and I'll say that if there exists a catalyst and there exists some thermal bath and there exists some unitary which conserves energy, such that I can do this transformation, that rho gets transformed into sigma s, then I'll call this, I'll use this notation with a catalytic thermal operation, right? So it's just, again, so it's kind of saying, so I'm interested in when can rho go to sigma when there exists a catalyst, okay? And so now we can return back to our basic question. So we had our basic question before, which is, well, which state transformations are possible under thermal operations? And now we can say, well, which state transformations are possible under catalytic thermal operations? In other words, you know, when is there a catalyst and a thermal operation where this works? And as I said, the kind of the beautiful result is that the catalysis really help. So for example, you can really write down states in relatively low dimension, where you can really show that rho cannot transform into sigma. So in other words, there's no thermal operation. So how do you know that? Well, you wouldn't satisfy these thermomajorization conditions from a couple of slides ago, or you don't satisfy this entire list of hypothesis testing entropies. So you know for sure that then there's no transformation. But what you can show is that then there does exist a catalyst where this works. So this is the nice result. And again, so for quasi-classical states, these class with no coherences between energy eigenstates, we actually have a complete characterization of which state transformations are possible. And this is from a very, say, another famous paper back from 2015 by Brendel, Horodecki, Nagy, Oppenheim, and Wehner. I think Nelly's talking later today. And they showed that there's now a different set of conditions, and this is why I liked writing the previous set of conditions in terms of the hypothesis testing entropy. Essentially what you see is that the entropy changes. So whereas before we had the hypothesis testing entropy, now we need to use a different entropy called the Renyi relative entropy, or sometimes people call it the Renyi relative divergence. Okay, I'm giving you the form here. The form itself is not too important, but you now have this infinite set of conditions now for all positive alpha, non-negative alpha. The transformation between two quasi-classical states will be possible if and only if this relative entropy, Renyi relative entropy, is larger in the state rho compared to the state sigma for all values of alpha. And just to say, I should have said this for the hypothesis testing entropy. I mean, one way to think about relative entropies are kind of like distance measures. So this is a bit like saying all of these different distance measures, how far is, or how distinguishable is rho from tau? So if, you know, the transformation is possible if and only if, according to this distinguishability measure or distance measure, rho is kind of more further away from being thermal, so more further out of equilibrium than sigma, according to all of these different values. This is kind of the way I like to think about it. So we have these two different notions of distance, and the catalyst changes your notion, which is relevant from the hypothesis testing to the Renyi entropy. Okay. And so this result is great. It guarantees the existence of a catalyst. So in some sense, this kind of removes part of the difficulty of the problem, because you don't have to go away and find the catalyst. But on the other hand, it doesn't actually tell us anything about the catalyst. And Patrick and I's starting point was that in some sense, we started asking ourselves questions about the nature of the catalyst that was necessary. And in particular, we wanted to understand, you know, how special are these catalyst states? So if there is a catalytic thermal operation where rho goes to sigma, well, how finely tuned is this catalyst omega c? Does it need to be a very, very specific state which is highly tuned to the pair rho and sigma, or is it essentially kind of arbitrary? Do many, many catalysts work? And related questions would to say, well, you know, is it the case that you can find small catalysts? So in some cases, you can really show, I mean, the very first example of catalysis that was shown, which was actually in the context of the resource theory of entanglement, is a very small catalyst. It's only a four-dimensional quantum state, and Plenio and Martin were able to show that this small catalyst was useful. But then there are other cases where the expectation is that the catalyst will have to be extremely large dimensional. So there's already an interesting question just to understand, say, how big is a necessary catalyst. But more generally, as I said, we were kind of interested in, you know, was the catalyst unique? Is it very special? And maybe it would be really great to understand what properties must it have For example, is it important that the catalyst is say a state of very low entropy? Is that the key property? Maybe it needs to have very high entropy. Maybe it should have a spread of energies. Maybe it should have, very we really, I would say I still don't have a great intuition yet, and our work, as I said, was just, I think, the first stepping stone in this direction. But our kind of overarching goal is to just really understand the properties of catalysts and really to get to the bottom of why catalysis works. What is it about adding in this additional state that allows new transformations to become possible? This is a kind of the broad picture that Patrick and I have kind of started, and we would still like to go much further than we've done so far. And this is why I'm kind of excited to hopefully promote this as an interesting question at this workshop here. And so our initial intuition, if I'm honest, is that catalysts should be very specialized. And maybe this came from a number of cases. So for example, when you think about cars, we know that catalytic converters are very special, and this is why people are now stealing them, because they're that these are rare materials inside that do the job. So it's not just anything works as a catalytic converter. As I said, if you take a very general view of catalysis, you can also think that tin openers are a bit like a catalyst, right? If I want to get into my tin of beans, it's very difficult without a tin opener, but as soon as you give me a tin opener, I can get in very quickly. And again, I don't feel like most objects would be useful for getting into my tin of beans, but I know for sure that a tin opener does the job. So our intuition was that somehow they should be very special, and our results are actually to the contrary, and that we found that generally what we seem to be seeing at the minute is that it's not the case, that actually generically, at least in certain regimes, catalysts are very generic. And maybe this is because we're considering kind of very large systems, and maybe that's ultimately where the power comes from, but this is, in my mind, still an open question which we would like to better understand. So just before I get into the details, when we started this, we initially started working with exact catalysis and doing some numerics just to kind of gain some intuition. And what we realized is that actually exact catalysis does appear to be too strong to answer this question. So, even in real life, the walls, of your piston, as the piston is going in and out, it does degrade very slowly. And what's really crucial is that the timescale over this degradation is just much longer than the timescale of the thermal machine, right? That you can do many, many cycles. So we do feel like it's justified in order to think about a slightly weaker notion of catalysis, which would then be approximate catalysis. And so what we are going to consider is, say, an approximate version of catalysis. And since we're going to approximate in two different ways, and both of them I think are crucial, but again, this is kind of an open question as to how much could we, say, restrict one of these two. And so I'll kind of add on an epsilon s for the system and an epsilon c for kind of two different errors, one on the system and one on the catalyst. Now, if there's a catalyst omega c and some thermal operation such that so I now apply the thermal operation on the system and a catalyst, and in the end, I'll get some final state, which I'm calling sigma prime S of C. And so what do I want? Well, I want that the state on the catalyst should be very close in say, trace distance, the most operationally meaningful distance. I want this to be very close to the initial state. So I want the catalyst to go back almost to where it was initially. And also, it kind of makes sense at this stage, if you're going to have a small error on the catalyst, what we realize is it also is kind of natural to allow a small error on the system. So you could think about this for thermal operations. In this paper by Reens that I was referring to earlier, looked at this idea of approximate thermal operations, where you say, okay, I'm not going to get exactly to the state I want. I might be interested in, can I get very close to the state that I want? That might be enough. And we know in general that these, most statements that we are interested in physics, you should allow yourself a small amount of wiggle room, and this typically makes your results much stronger. So this is a regime that we worked in. And so, as I said, yeah, we allow approximations in both the system and the catalyst, and we would recover exact catalysis if I were to demand that this final state, the sigma prime of system and catalyst, was indeed the tensor product state, sigma of the system, tensor omega of the catalyst. And so this does introduce there's a subtle point here, which I just want to emphasize, which is, on the one hand, how would I recover this limit? Well, I clearly need to take both the error on the system and the error on the catalyst to be equal to 0, but actually this isn't strong enough to recover this. I also require that there's no correlation between the system and the catalyst. So we are also, the third thing that we've actually allowed in this definition is that we've allowed a small perturbation on the system, a small perturbation on the catalyst, and we allow some amount of correlation to build up between the system and the catalyst in the process. So this is the regime that we're going to work in. And there has started to be a bit of interesting, or a bit more interesting catalysis in recent years, and this does seem to be a natural regime where lots of interesting results are popping up. So I think this is a good notion of approximate catalysis. Okay, so one final caveat is just to say that we really have to be careful about the size of this error. So I talked about these errors, say epsilon catalyst and epsilon s, but we really need to think about the size of the error in relation to the dimension of the catalyst, actually. And so on the one hand, imagine that we didn't care about the dimension of the catalyst. Imagine we just took this, we just demanded a constant size error. Well, it turns out then, and this was shown in this, again, in this same paper from Pinas, that all transformations actually become possible if you only demand that the catalyst is returned with a constant error. So in other words, you can take a very, very high dimensional catalyst and you can make the error in the catalyst as small as you like, but actually any transformation becomes possible. And so in some sense, I mean, this means that the theory becomes highly unconstrained. So kind of any two states can be transformed into each other via some catalytic thermal operation. And you might argue it doesn't really feel exactly like the thermodynamics we were looking for. We want the second law to have some content. So this is kind of a regime which is not the most interesting regime. And actually in another paper by Nelly, also with Manchinska, Kirstau, Iser, and Wehner, they actually found a bit more precisely that the bound on this error of the catalyst. So actually they were able to show that the kind of the most difficult state transformation becomes possible by optimizing over the catalyst exactly when the error is larger than this value. So it's not too important, but it's just interesting to note that it's scaling like 1 over the, log of the dimension, which if you, morally, this is a bit like the number of particles in the catalyst, right? Log of the dimension is kind of counting particles. So this is an interesting bound. And we'll need this bound later on in the talk, which is why I mention it here. And the fact that the all transformations become possible if you allow the constant error to become constant, well, actually, this was something which was kind of first understood in entanglement theory. And in entanglement theory, this is known as entanglement embezzlement. So it's known that you can kind of borrow a highly entangled state, and if you only have to return the state with up to a small perturbation, then essentially you can do any transformation in entanglement theory. And so, not surprisingly, you get the same kind of thermal embezzlement in the context of the quantum resource theory of the resource theory of quantum thermodynamics. So yeah, this is one regime, but there is an interesting regime, a regime that I find particularly fascinating. So if you do allow slightly stronger than this bound, so if you take the error in the catalyst to be exactly 1 over the log of the dimension, so you take it to be basically 1 over the number of particles, as the catalyst gets bigger, you demand a smaller and smaller error. Then what you can show is that a catalytic thermal operation between rho and sigma is possible if, for quasi-classical states, this is if and only if the free energy, the generalized quantum free energy of rho, is larger than the quantum free energy of sigma. So this is kind of beautiful in many ways, because you get back what you would call the kind of the natural second law in this regime. And just to say, so what is this free energy? Well, it's the difference between the average energy of the state, so the expectation value of the Hamiltonian, minus the temperature times the von Neumann entropy of the state, right? So it's, E minus TS. So you could, this is essentially the quantum free energy. And so just to say, where does this come from? Well, it just so happens that this expression is equivalent to one of the Rayleigh entropies when you take the parameter, the alpha parameter from previously equal to the value 1. So in other words, you had this infinity of conditions for all alphas, and all of them become irrelevant except for the one of them which remains. And it happens that the one that remains is, you can interpret it in this free energy way. So that's kind of mathematically how this arises. Yeah, and so this is why we kind of say that the second laws collapse. So this infinity of laws collapses back to just one standard second law. And yeah, the details can be found in the PNAS paper. Okay, so that was a lot of background. And now let me talk about some of our actual results. And so I'll talk first about the analytical results that we have. And this is on a multi-copy catalysis regime. And so what we wanted to consider was a situation where the catalyst is a large collection of identical particles, right? So in other words, I'm going to give you, say, n qubits or n two-dimensional systems, all in the same state. And we wanted to more or less focus on the case when n is large, right? So kind of a large catalyst, but where all of the states are identical. And we were interested then in which states, of this small system, so which states omega c are useful catalysts when n is large. So this is the question we ended up focusing on. And our intuition, why we think that this was a good case to work on, is because we had the following intuition, is that in the asymptotic regime, we know that state transformations become reversible. And again, this is, this was the main result of the first paper on the resource theory of quantum thermodynamics, where they showed that if you give me any, say, n copies of some state omega c, I can transform it into some other number of copies, m copies of some other state omega c prime, and I can do this reversibly using thermal operations. And so once you have this realization, then you realize, well, you say, well, if I give you many copies of a state and there exists one highly specialized catalyst, well, now what I can do is I can just transform many copies of some arbitrary state into some number of copies of the specialized catalyst, right? And then I can use the specialized catalyst in order to do my catalytic thermal operation. And because it was catalytic, the intuition is that I should then be able to reversibly transform back my useful catalyst back into the original state. So this is the basic structure of our proof. Was a protocol of this approach. So kind of we called it pre-process to kind of turn the state into useful, then do some selective but interesting catalytic thermal operation, and then kind of post-process it back into the original catalyst. And everything was approximate, and so that the hope is that everything works out here. And if everything pulls together, then the full process looks like it should be catalytic. So this is essentially what we were able to do. I will just give one caveat here, which is to say that unfortunately a couple of weeks ago we did find a gap in our proof. So as one of our lemmas that we rely on was actually unnecessarily strong. We kind of realized after the fact. And so it just isn't true. So we will be posting a correction to the paper at some point soon. And at the minute, Patrick and I are working on fixing this error. So not fixing the error, on bridging the gap. So our intuition is still that everything holds together and that we just need to replace this step in the middle. Well, essentially it's this first step. It's the transforming step at the beginning. The explicit lemma we use in order to show that we can do this isn't quite correct, but we're just in the process of doing the analysis. So I still want to talk about the results because I'm still confident that everything fits together, but I just give you this caveat now that there's a small gap, unfortunately, but that's life. Okay, and so we have kind of two versions of the result, which I'll mention. So on the one hand, we got a first result in the embezzlement regime, so this slightly less interesting regime. And you'll see the protocol is kind of very naive in some sense. But it was good to see that the basic idea got us somewhere. And then I'll show you afterwards an improved protocol which Patrick found, which goes further. And so what is the main idea in the embezzlement regime? Well, we imagine we're trying to get to the transformation we want to achieve is rho goes to sigma. So why don't we just transform our catalyst, which was n copies of omega, into some number of copies of the target state itself? So we know how to do this in the asymptotic regime. So let's just assume we basically prepare where we want to get to. And now let's imagine we do this kind of mixing operation. So I'm going to do a thermal operation, which basically probabilistically swaps rho with one copy of the catalyst particle, one of these M copies that I've made. So at the end of the day, I get a state where kind of the rho is kind of hiding in one of the catalyst states. And so as a picture, I would start off, say the crossed element is rho, and then I've got all my catalysts in the same state. I've done this transformation, they're all in the state sigma C. And now I'm gonna end up mixing them so that the element, the rho is with probability 1 over n plus 1, it's remained rho, probability 1 over n plus 1, it's the second system, etc., etc. Right? So a very kind of naive protocol. And so luckily for us, this is what Patrick realized, is that there was a nice result from a few years ago by Anshu Devabathini and Jane in PRL, which is the so-called convex split lemma, where they actually were studying this map in a slightly different context, in a communication context, but it's nevertheless the same map. And they were able to show a nice bound on the trace distance between the output of the map, so this final state here where you've kind of hidden the state rho, and the kind of the state that you would like to achieve, right? The state where you've actually just got the final state is sigma, and the catalyst has remained sigma tensor m. And what they show is that this is never larger than this number 2 to the d infinity. So this is one of these, again, Rayleigh entropies. Now you let alpha go to infinity, so this is just some number, and you take 2 to the power of it. But crucially, you see we get to divide by m. So as I take m to be larger and larger, I can make this error go down. And this is the trace norm squared. And so this is decreasing, like the trace norm is decreasing like 1 over square root of m. And so if you go through the details, and I'm not going to go through them in this talk, what you find is that the error on the catalyst then scales like 1 over the square root of n. The error on the system scales like 1 over n. And just to remind us that the dimension of the catalyst, because I'm starting with n catalyst particles, it is some d to the n. So if you were to go back to this, think back to the slide I had a couple of slides ago, this puts us in this embezzlement regime. So the error is dropping with n, but it's not dropping fast enough on the catalyst to make so that basically all transformations are possible here. So this catalyst this idea is kind of useful. Anything can work as a catalyst in this embezzlement regime, but this is not kind of as strong as we wanted yet. We wanted to go beyond this regime. And you see that the main thing was, okay, this was just one choice for the target catalyst. And so our goal at this point was to try and find a smarter choice. And so Patrick really did find a smarter choice, which was which works in the genuine catalysis regime. So in this regime where really there are non-trivial kind of second laws governing your state transformations. And something which has come to be known as the Dwan state is actually a much better target state. So now instead of transforming into, say, your final state, you should actually transform into a smarter state, this so-called Dwan state. And I've written it here. It's a bit hard to pass this formula, but as a picture, you can hopefully get some intuition for what this state is. So it looks a bit like this. So this final register on the side is kind of think about this as being a flag. It just tells you which of these different states you're in, and your kind of equal mixture of these different states. But what you see is that you're a mixture where, on the one hand, in the top line, every single state is the target state sigma. So this is a bit like what we chose in the previous slide. But now we say, well, let's not just take this where all states are sigma. Well, let's take it where some of them, all but one of them are sigma, and one of them remains rho. And we'll take this mixture going all the way down to the bottom where all of the states are rho, right? So a priori, this isn't obviously an interesting state to take, but it turns out that this is a very powerful state, and it's powerful in many contexts, even beyond our results. I think this state there are lots of papers appearing at the minute all making use of this state because it's a beautiful construction. And so let's see how it works. So why is this state powerful? Well, let's for the minute assume that there is a thermal operation which works at the multi-copy level. So what I mean is that imagine that it was possible to find some thermal operation which transformed m copies now of rho into m copies of sigma, right? For some m, some finite m. So I'm just going to park this for the minute. Let's just assume that such a thing is possible. Then what you can show is that actually, if I give you one copy of rho and I give you this Dwan state, then there exists a thermal operation which will transform perfectly catalytically rho into sigma using the Dwan state. So this is the beautiful result. And actually, it's pretty nice to see, and I'm going to try and sketch graphically how this proof works. So let's just take the initial state. So if I take rho tensor omega, so because this was just a mixture, it amounts basically, I just need to add a column here of rows at the beginning. Remember, rho was the one with the cross. So this is the initial state. And so what's the first thing I can do? So if you look at the bottom row here, I've got a row of rho, I mean, the bottom, sorry, row is all rows, rho, the Greek letter rho. And so what I can do is I can say conditional on the register, on the flag being in the state M. Well, I can now just do that operation, which I assume existed, right? I said assume that there exists a thermal operation which can take M copies of rho into M copies of sigma. And so the first thing I can do is I can just change the bottom line into all sigmas, right? So this is a conditional thermal operation, which will do this. So this is step one. And now I'm in this kind of messy state. But now what I can do is I can now kind of look the other way. I can look at these at the columns, and I now notice in this, is that right? Yeah, which way around? Sorry. So now what I can do is I'll also again look at rows, and I'm actually going to flip so that I'm going to take the bottom row and I'm going to pull it up to the top. So I'm just going to permute my labels, and that will have the effect of changing all these rows. So the one which is all of this without crosses, it was initially at the bottom. Let me just pull it all the way up to the top. And now I've got this, so this is some unitary which will move it up to the top, right? So this is an allowed thermal operation to move this up to the top. Now I'm looking okay, and now I can switch my perspective, and I can instead focus on a row. And if I focus on this second row here, I see in every single case I have a sigma, right? Because all of them are sigmas because there's no crosses here. And so what I need to do is another permutation. So I'm going to pull this the system state, and I'm going to permute it so it becomes the final state of the catalyst. So I'm going to swap, I'm going to kind of shuffle everyone one to the left, and then if I do that, I end up here. And now if you just have a look, you see that this is exactly the same at the level of the purple, so the level of the catalyst. I've got back exactly the catalyst from the top here, so I've got back my Dwan state. And if you look at the first column, well, I've transformed from having all crosses to all circles. So in other words, I've transformed from rho into sigma. So this is this kind of very beautiful protocol which uses this Dwan state. This is what this paper of Dwan co-authors realized, is that this protocol works. And so indeed, this shows that assuming you can do a multi-copy transformation, then this catalyst is essentially the catalyst you should use in order to do it at a single copy level. And so what they also showed in the same paper is that for quasi-classical states, when does this multi-copy transformation exist for some finite m? Well, they actually showed that it is exactly the same condition as the condition found in the catalytic for the second laws. So it's exactly the same condition using exactly the same relative entropies. So if for quasi-classical states, all of these distances as measured by the Renyi entropy are bigger, then you can do the transformation. And so you put everything together, and you get now exactly into the genuine catalysis regime. So you get the error which drops exactly as you want, both on the catalyst and the system. And so this gives you this very nice result. So everything kind of holds together. Modulo, as I said, there's this gap currently in the proof, but we're just working through the details, but everything looks like it's going to fall into place. It's just we're just having to kind of turn the handle at the minute, and we're not quite finished yet. Okay, and so let me then just in the last 10 minutes or so talk about the numerics. So that was kind of the analytical type results we had, and what we really wanted, where we actually started, was just to think about high dimensional catalysts, but we kind of, well, we got stuck and we weren't able to finalize analytical results for high dimensional catalysts, but nevertheless, the numerics are very promising in this direction. And just to say for the minute, just for all of the graphs I'm going to show you in the coming slides, we're going to consider just a toy example where actually, say, all the Hamiltonians vanish. And this is a resource theory, which also has a different name called noisy operations resource theory. So it's kind of a baby version of thermodynamics. It doesn't change. We investigated and it doesn't change the results. And there's a so-called embedding map, which shows in some sense that the results are formally equivalent. But for the minute, we're just going to work in this regime just to keep our life a little bit simpler. Okay, and so what are we going to do? So we're going to start off. I'm just going to pick a fixed rho and a fixed sigma. So I'm going to pick two Q-trits, so 3-level systems, and we pick them such that on the one hand, rho cannot go into sigma, so without a catalyst, on the other hand, such that rho can go to sigma with a catalyst. So a catalyst is required, so it's a kind of a non-trivial state transformation. But on the other hand, yeah, so that's what we're going to consider. And then what we started doing is we then wanted to sample random catalysts, right? So we wanted we chose some probability distribution over positive numbers, and we picked, say, if the catalyst is DC dimensional, we just picked DC numbers, and then we normalized. And so this is just a kind of a very bog standard simple way of just sampling random catalysts, right? So we just made random diagonal catalysts. So these numbers were then the diagonal entries of the catalyst in some basis, and this is how we chose it. And we considered 3 different possibilities in the end, just to kind of see how the probability distribution mattered. So on the one hand, maybe the most natural distribution would just be to take the uniform distribution. So we just pick probabilities at random, and we'll see how that behaves. We also picked an exponential distribution. So we got a different spread of eigenvalues. And we also considered this Rayleigh distribution. I can't remember why we considered this. Oh yeah, because this one is bad, as you'll see. And so our question is how frequently does a randomly chosen catalyst catalyze the transformation rho to sigma for a fixed error, right? So we want to somehow think about this as a function of the error. We wanted to know, what fraction that we just pick catalysts at random, we get frequencies, and some of them will catalyze it and some of it won't. And we just wanted essentially to find this value. And so this is what we found, for example, with the uniform distribution for 3 different sizes of catalysts. So when we took a 16-dimensional catalyst, so another 4 qubits, as we say increase the allowed error on the catalyst, then we got an increase. So it becomes easier as the error gets bigger, but it's saturated. So around just above 80% of the catalysts of 16-dimensional catalysts were useful for this transformation. And this plot here this is just a plot of the eigenvalues, the histogram of the eigenvalues of the catalyst for a uniform distribution. So we get this kind of relatively narrow drop off in the size of the eigenvalues. And then when we increase the dimension, so we went from 4 particles up to 6 particles, then we see that as we increase the error, now the probability that a catalyst is useful now actually goes up basically to 1, well, just below 1, you see, quite rapidly. And when we went up, so that was 4, 6, and we went up to 8 qubits, again, there was a slight improvement here. So indeed, this was kind of our first numerical investigation, which said that high dimensional catalysts seem to be useful, at least for this one pair of states, rho and sigma, that we looked at. And we looked at a few, and this did seem to be representative. And I'll come back to this in a minute. Now, if we look at this exponential distribution, so if you look here, we get a very different kind of histogram of eigenvalues of the catalyst. Now the situation changes quite a lot. So even now for 4 qubits, we see that we basically get up to 1 when the error is large enough. Basically every catalyst works. So this is in contrast to the uniform sampling. And also, it's much more rapid if you look at, if I go back, you see it's much more rapid compared to the uniform distribution for 6 particles and for 8 particles. So this is actually the best sampling we found, was sampling according to this exponential distribution. So we don't know why, but that's something that we've observed numerically. And then on the in the opposite direction, if we went to this Rayleigh distribution, we saw that this is actually terrible. So we get this kind of weird distribution of eigenvalues here. And actually, you see that even for 4 particles, the probability of working is terrible. It's about half of the catalysts we sampled were able to catalyze for 4, and even for when we were considering 8 particles, still only around 80% of them were actually able to catalyze. So this is a bad sampling. In comparison to the exponential, what we can see is that the distribution of eigenvalues of the catalyst does make a difference, and one should sample kind of preferentially with this type of distribution. So this is the message in this first instance. So that's kind of good, but ultimately that was just for a single transformation. And what we really wanted to understand is how generic this is. And so then Patrick had this idea to say, well, let's consider fixing the initial state rho. So we'll always consider one initial state rho, and let's think about all of the possible final states that we could go to. And so if we consider Q trits, so when d is equal to 3, and we consider quasi-classical states, so states which are diagonal in the energy eigenbasis, a nice thing is that actually all states can be represented as a point in the probability simplex, right? So I can consider the projectron to 0, the projectron to 1, and the projectron to 2, and any, say, 2 states. Imagine I want to go from rho to sigma. Well, any state rho that's diagonal is just some point within inside this simplex, right? It's some within the convex hull of these 3 extreme or pure states. And so what you can do is we can then, Patrick said, well, let's fix the state rho and let's think about every single point in this simplex as the final state. And what we will do is we'll fix an error, and we will ask what is the probability that a random catalyst works in this case. Sorry, let me go. I have to go a little bit slower. So there are 2 sets which are interesting. So within this probability simplex now, once I fixed a rho, there's going to be some region in this space, which I'm going to call S of rho, which are all of the states which I can actually get to via thermal operations. So these are the ones where I don't need a catalyst. These are the states I can get to. And on the other hand, there's going to be a set of states which I can get to via catalytic thermal operations. And so this is kind of our target state set. This is a set that we know that there exists a catalyst. And now we can try to understand, well, within this set, how well do arbitrary catalysts do if I pick an arbitrary catalyst? So this is what we do. So we want to understand how much of this catalytically accessible set, T, does a random catalyst recover. And so this is our result. So the black dot is rho. So this is the state we considered, this point here. And we tried to figure out what are the, what do we do? So this dotted triangle, this is the S of rho. So this is the set which I can get to via thermal operations without a catalyst. This bigger curved region is the region I can get to given some catalyst. So this we can check using the second laws. And now what do we plot? So we're now going to plot in color the probability of success once I fix the error. So we fix the error, this bound on the error, the embezzlement bound, we took it to be 1/10 of this bound. So we're kind of way away from the regime where it becomes trivial. So this is to kind of make sure the results are non-trivial. Now for each point, then we sampled randomly catalysts according to this exponential distribution, and we're coloring it yellow if it was essentially if all the catalysts work, and then we go down to 0 when none of the catalysts work, right? So this plot is like yellow is good, and as you get away from yellow, it's bad. So basically you see that in this region kind of close to the region where I could achieve without a catalyst, with high probability, catalysts are working basically with probability 1. This is again with 4 qubits. And as I get towards the boundary of the set here, you see that there's this region. So if I tried to do this transformation and I picked a random catalyst, you see essentially it doesn't work. So there are no 4-dimensional catalysts which would allow me to do this transformation, even though there does exist some catalyst which works. And just to say this little point here, this is actually the sigma from the previous plot. So rho to sigma was the transformation we considered. So we considered something which is kind of quite far away, and that this is its representation here. So this was with 4 qubits. And what happens now when you go up to 8 qubits? So we actually get a nice thing. So you see like the yellow region expands, and essentially everything within the catalytically accessible region has has more or less become yellow. So this is great. This is seeing our kind of universality. So we're increasing the dimension, and essentially any catalyst we pick is able to do the transformation. And just if you're wondering why am I outside this region? Well, this is because we're considering approximate catalysis, whereas the solid black line is exact catalysis. And of course, the point is we don't know the boundary for approximate catalysis. That's a very hard boundary to understand. We only understand the boundary for exact, which is why that's the one I plotted for comparison. But interestingly, you see it doesn't go beyond. In these regions, it doesn't go beyond the exact catalysis bound. So it's not that the approximate catalysis has kind of encompassed it. It seems that the boundary is the same. And again, this is something we don't understand. And it would be great to try to understand why that's the case in future work. Okay, and so now finally, the above was still only for a fixed initial state rho. And so the last step is just to think about, can we say something about an arbitrary initial state? And so we can do this. So we can think about, we can give a name to this region, this kind of bit which is outside this region which is inside T, but not in S. So call the difference between the two, let's just call it D for the minute. So it's this region which is the catalytically accessible region. And what we ask then is what fraction of states inside this region have a success probability larger than some fixed amount. So let's say larger than 90% or 95%, something like that, right? So in other words, the final question we asked is how likely is it that a catalytically accessible transformation can be performed with high probability using a catalyst of some dimension DC. And yeah, this is a bit of a mouthful to say, but this is kind of inspired by kind of when some people do machine learning, they do this probabilistically, approximately correct machine learning, and this has a similar type of flavor. It's with high probability, you can do an approximate catalysis. So this is our motivation for this definition. And so this is then the region we get. This is then the final plot we get. So now each point is so now I think each point corresponds to an initial state rho. So say this point here in yellow that I'm pointing to, this would be a state rho, and then that would define some region of this catalytically accessible region. And now we're asking, within that catalytically accessible region, how much is accessible, how much was yellow basically in the previous plot, how much was close to basically having probability 1 of using a random catalyst. And so you see we get this kind of bizarre structure. So there are some points already out at the boundary where basically random catalysts are very useful, even when the catalyst is only 4 qubits. But then there are these other regions here where if I want to do a transformation of this state, then essentially none of the probability of a random catalyst being helpful in that region is basically 0. So basically none of the transformations which need a catalyst can be done with a random 4-dimensional catalyst. This is what this plot is saying. And so that was for a 4-dimensional catalyst, and then again we were able to do numerics that was for a 16-dimensional catalyst. We were able to go up to a 256-dimensional catalyst, and again this yellow region is growing. So we're seeing that again this is really the universality, showing that with high probability, in all of this region, a random catalyst is going to help you, which I think is a good message, a good take-home message here. Okay, so I have a couple of minutes left. Sorry, I'm running a bit over, but so what is a summary? So I think our analytical results, modulo this caveat, show that if you give me sufficiently many copies of any state, then it acts as a catalyst. So this catalytic property is relatively universal. This is the way we think is a good way to phrase it. And maybe much more general than I think maybe people had expected or understood before. So that's what I think is most exciting here. And just to say, I've talked here exclusively about quantum thermodynamics, but actually because of the way we've done things, everything I've said is essentially very general with regards to kind of quantum resource theory. So if you have a quantum resource theory and the allowed transformations are dictated by some majorization condition, then essentially our results will also hold. So that is a nice thing, that this is not just about thermodynamics. It would also hold for entanglement theory or other theories where you have a majorization relation. And I think our numerical investigations are really show that this, beyond this multi-copy scenario, we really have this universality is really generic. So when you have high dimensional systems, they really do seem to generically act as catalysts. And that, for me, I still find that a little bit surprising. I don't know if I really would have guessed that would be the case when we started this. And so just mention very quickly the big questions. So I still think that the mechanism we don't really understand. Although we started this project, the question we would really love to understand is what is the, how does the catalyst work? And what are the physical properties that are relevant? I think we've got some first indications of where to look, but we definitely don't have an answer to this question. So this is, for me, would be what I would really love to understand in the coming years. I would also like to, extend our analytical proofs and finish the fixing the gap in our current proof that basically high dimensional states are universal catalysts. We didn't yet find the right tools to do this, but I'm sure I'm sure if other people get interested, they might be smarter than us and they might be able to do this. I would also really like to understand the role that the correlations and independence play in catalysis. So there's been there's been a few results recently about this. And as you saw, we needed to allow for approximate catalysis, and it did seem that we did need allow these correlations to build up between the system and the catalyst. So I don't really have yet a good understanding of how important these are, but I think this is really would be a very nice thing to understand. And also, as you would have appreciated, hopefully everything I talked about today was with these quasi-classical states. And so I haven't really touched at all on situations where you have coherence between the energy levels. And there our understanding is basically much less advanced than in the case of quasi-classical states. And I wouldn't like to bet how things change. I would hope that things are still relatively similar, but I think that's a really interesting question to investigate. And also, just more generally, we would like to understand if this universality holds in non-majorization-based resource theories. So beyond quantum thermodynamics, there are lots of other resource theories which are not governed by majorization at a fundamental level, and we would like to extend our results there too. And so with that, I say thank you very much.